Hello and welcome to our next session of Research and Academic Skills. And we are into the second half of this module. And things will slightly change. In the practicals, we will work in groups on the assessment. And on the theoretical side of things, this week is essentially the last week of what I would call truly exciting theories, remotely related to what we do. And then the lectures will become increasingly more application-oriented. So yes, probably, as far as I'm concerned, probably the most interesting lectures are this week, as we discussed complex systems. So as a matter of introduction, we've come to the point of having explored, in general, the essentially causal approach to science, whereby we have facts, rules, kind of strict science in the way that it was conceived centuries ago. And then increasingly, as we improve our scientific findings, we come to understand the limitations of this historical approach. And that's the birth of complex systems, which is by now very large domain of inquiry and probably the most exciting. So first, what is a complex system? Well, it is a property of the system which kind of indicates that simplifying it does not really explain it. So the point is that the reductionist approach of separating into smaller parts, analyzing the parts, this approach fails. That's the main characteristic here. And nevertheless, we can conceive of these systems as being made up of distinct parts, units, agents. And indeed, if we model such systems by creating a lot of densely interconnected units, then we have already at our disposal many properties of complex systems to observe. Indeed, with very simple algorithms, we will already see some complex behavior emerge. So the first two things that I will mention, there's many different properties that we can talk about and will do. But the first most important one is adaptation. So complex systems typically adopt to the environment, and they internally adopt as well. So they're kind of dynamic in that sense and almost responsive, you could say. And the second important property to start with is what we call emergent behavior. Or emergent property at times as well. So what this is a phenomenon whereby the interaction of units produces form, regularities, behaviors that we cannot attribute to separate units. Okay, so it is the situation whereby the group, the densely interconnected group, becomes more than just an addition of elements. Okay, and this is quite interesting also in arts. There is a sense of a piece of art having this emergent property in the sense that it is more than just the sum of its components. Okay, so let's look at basic examples here. You might be surprised there's quite a few. First thing, water. Okay, so here already what we have is that the behavior of water as a liquid is not easy, or probably not even possible to explain just by looking at each molecule. So it is about the interaction of molecules, and therefore it is emergent behavior. Okay, as far as the adaptation goes, it is clear you can pour water in different vessels. It will take on different shapes. Okay, another property that water has, which is typical of complex systems, is that it has different phases, or as we say, different aggregate states. So the elements remain the same, the molecules are the same, but depending on temperature, we might have ice, water, or vapor, which highlights how the overall structure is much more complex than everything we can say about its components. Supposedly, proteins as well, the way that molecules arrange into amino acids, basic biochemistry is full of similar examples. I mean, if you just think of life itself, can we explain it from just the chemistry? By looking at the components of matter? Indeed, it seems that we can't. So again, we have an emergent property. We have adaptation. Life is a prime example of this. Similarly, we have great advances in neurology recently. Nevertheless, we still cannot connect the dots, so to speak. So if we look at the functions of neurons, we still cannot understand the function of the brain, which is technically just a collection of neurons, but indeed it has some emergent properties that go beyond the properties of elements. Similar structure that we can think of is society. Okay, so again, we have smaller elements, we have people, but when they interconnect, we get properties which cannot be explained just by looking at separate people. So again, the reductionist approach fails here as well. And we can go on with the list, evidently, biosphere. So what you see here then is that if I take proteins, brain, society, biosphere, they're actually built on top of each other like that as well, right? Because a lot of brains make the society, a lot of societies make the biosphere. I mean, a lot of proteins make the neural cells and so on. So you see that actually what we have is multiple layers, and at every next layer we get a different game, so to speak. And therefore it is almost impossible, at least at this stage, certainly impossible, to connect all the dots in this way. Now I've kind of built it up from bottom up, but actually the interesting thing to observe is that we can produce a good description of the whole also by going top down. Okay, so bottom up, top down operational principles mix very frequently in complex systems. So typically there is a bottom up, top down, how should I put it, control, right? Although if it's controlling both sides, you cannot really say that the higher phenomenon controls the lower ones or other way around. But nevertheless, we tend to use the concept of control for lack of better paradigm at this stage. But in any case, typically in the brain as well, what you have is that you have a higher level phenomenon, which is awareness, which can actually control lower level activities. So with my awareness, I could make a choice that will change the functioning of the neurons, but at the same time, the neurons come together to produce this awareness and intelligence. So there is a two-way interaction going on across these levels of organization. Okay, so it's interesting also to think typically from a human point of view, people make up the society, but actually you could also argue that society brings about humans, individuals. In fact, society is gonna outlive each and every individual. In that sense, it seems to be a more stable phenomenon than a single individual. So in that sense, in each of these systems, we can argue both ways. And then, obviously, the connection to computing, we have complex systems in computation, and we will look at some of the examples there. Now, if you're interested in this domain, it is very rich. There's a lot of recent findings. Here is a sketch of key terms if you would like to look around and study some of this. I can largely recommend it. We don't have the scope to go into details here. So we're scratching the surface and essentially introducing the domain. Okay, so here we have two axes, academic applied, left to right, and technical to non-technical, bottom up. So typically I'm going to discuss the academic and more technical side of things in these two lectures because they kind of form the foundation for the others. However, I imagine many of you might be excited by application more than theory. So I invite you to study further using these keywords. So in essence, looking at the bottom left, complexity science, typically many topics to cover, which I won't have the scope for, but I will talk about networks because they are kind of the simplest approach and an approach that will already yield a lot of complex properties. In the meanwhile, I've been talking about evolution, hopefully in every lecture it comes to mind one way or the other. So that will be our introduction, briefly about nonlinear systems, what does it mean, and so forth. But just to touch briefly on the others, I will mention a few principles of designing complexity, which has everything to do with creating systems that adaptively grow to do the task. Okay, so you kind of assume that an adaptive growth, an evolutionary process, will optimize the solution over time and thereby produce a better solution than a solution that we could design. So it is a kind of a departure from very strict design into producing adaptive systems, which is quite exciting. I mean, in a way, this is something you can already imagine happening. For example, your assessment, where you will work in a group of 4 people, there is only a basic distinction of roles, as you will learn. But the point is that I expect the complexity to arise from the interaction of the members of the group. So in a way, it is a similar approach in that it is not thoroughly designed, the system, but it is left to its own devices to adopt and to produce solutions. Okay. So in a sense, I've actually talked more about systems thinking now than systems design, because I'm talking about it and I'm not doing it, right? So I'm still on the academic half. But in any case, the point here is to just give you a general idea of what we're looking at. And then the top right corner, what you see there is non-technical applied aspects of complexity. And here typically we have either social theory or organizational theory, borrowing some ideas and terms from the technical side of complexity. And it's a set of key terms for you to look up if you're interested in how essentially thinkers about society, about organization, management, and similar things have adopted these ideas. Okay, so first thing we will look at are networks. So the interesting thing here is that we already will see a lot of, if not all the properties of complex systems, which are as follows. Emergence, as I've explained just now. Phase transition. Okay, so I've hinted at that. Phase transition, you can easily remember if you associate this with ice, water, and vapor. So what we have is the same set of elements, but a totally new behavior that suddenly emerges based on the environmental factors. Okay, so you could also imagine a harmonious family getting into a fight, for example. So you actually have a sudden transition to a completely new configuration of the same elements. Okay, so that's very typical of complex systems. The other thing which is most often the case is that there is no centralized control. Okay, so again, if you think about water, obviously there is no command which instructs the water molecules to become ice or vapor, but the interaction at local level changes, okay, based on the temperature. Molecules interact differently. And then this local change will produce a global change, a global phase transition. Okay, so you can also think, for example, evolutional terms going from, nomadic lifestyle to agriculture. And you also see what is quite interesting and often the case is that distinct or isolated systems will go through the same phase transition. Okay, this is also the case with a lot of scientific discoveries, that it seems that different people almost at the same time develop the same new theories and innovations. So in that sense, we see how there is a tendency of the system to develop, which seems independent of the elements of that system. Okay. Nevertheless, there is no centralized control. So it's kind of really evasive like this, because you would typically imagine that if there has to be a global change, there has to be a central source of command to induce a global change. But complex systems show us that this is not the case. The system evolves itself in the ways we're looking at. Okay, I've mentioned the fact that reductionism fails in explaining these systems. Adaptation is a crucial property. And it's interesting to consider this because I will not go into computational algorithms to a great detail. I imagine you will study this if you haven't already in terms of artificial intelligence neural networks. But the interesting thing is that what we can do is we can model adaptation in how it operates, in how it appears. So we can, so to speak, symptomatically copy the behavior. So we can program a system which will be adaptive. Okay, so typically you can think of control systems theory here. Segway, which is a kind of a real-time control system. You probably know what I'm referring to, the kind of vehicle with two wheels, where if you lean forward, it accelerates, you lean back, it brakes, and it keeps you in balance, or at least helps you stay in balance. So that is actually already a kind of a deliberately adaptive system. And it's actually produced using recursion, using feedback based computation. Okay, we'll look at some of these concepts. The interesting thing is that you will also achieve adaptation without deliberating it. Okay, so that's the characteristic of complex systems, that typically the properties grow out of the interaction within the system, and you don't necessarily design the system for it to have a certain property. The properties arise from the internal organization. Okay, so you could probably program a Segway without deliberating adaptation using a neural network, which is more of a black box rather than a set of procedures, which is more transparent. Okay, so self-organization, I've been using this concept already. In a sense, the adaptation within system actually produces higher level properties. Interesting phenomena occur with networks. They can learn. Okay, so you probably know some detail about face recognition algorithms, typically achieved with neural networks. And the interesting thing here is that the amount of detail that a network can learn surpasses our expectation in terms of information theory, which I won't talk much about. But it is kind of stunning how much a network can learn on top of existing knowledge as well. It shows how the idea, I've talked about the memory paradigm, if you remember. So this kind of links there that essentially the complexity of interaction is the storage, because there is no storage, there is no memory, there is no content, there is only adaptation. And in adaptation, what we have is an increasing number of patterns, behavioral patterns, which seem to multiply without delimitation, which might be predicted from the units, right? So you would say, well, a network, a neural network, a small one, has a very limited amount of coefficients, but it can actually learn many more things than the amount of coefficients that it has, if I'm to put this simply. Okay, and then at the top of this scale, what we find is self-reproduction, which is far out, as they say. The fact that a complex system has a way, might have a way of producing another version of itself, another little complex system. So obviously in life this is quite apparent that we have reproduction, but actually in some domains of human activity we might find traces. You might be aware that there are algorithms that reproduce themselves already, and in a way we also have a great interest typically to produce the production rather than the artifact. Okay, so in that sense we have manufacturing, which is kind of a basic reproduction based on copying. But we also have kind of next level generative art, where we are essentially producing these more complex relationships without designing it specifically. Okay, so I'm going to talk a bit more about networks. I have to be very careful because this is my favorite topic. I can talk forever. In fact, I'm way past the half time here. So just briefly for your reference, we have different topologies that we can relate to, different properties of different networks that resemble these shapes. Typically fully connected graphs are a good starting point. And graph theory is the key term here. So there is a mathematical description of networks that is quite fascinating if you can grasp it. If it is your cup of tea, I can suggest to dig into this. So what are the properties of the networks that are complex? Okay, so first of all, there is a problem with predictability, which is also the case for chaotic systems, which will be the topic of next lecture. In essence, it is unpredictable. Now, in complexity theory and chaos theory, you will often find the concept of unpredictability. And it may be confusing because some of these systems may indeed be very simple and deterministic. Okay, I can in fact produce a recursive equation with only one variable, 2 additions, 1 multiplication. Very simple equation. If I make it a recursive equation such that the result of a single calculation becomes the starting point for the next one. So in other terms, if I put the equation into a feedback loop, what I get is a deterministic system, right? So there is no randomness. It's just essentially a quadratic equation, typically. And what I will get is the situation where I can run the model, I can run the algorithm, but I do not have a shortcut to predict the outcome after many steps. Okay, so if I have a non-recursive equation, if I just say y is x squared plus log x minus 1, or 1 minus x, probably funnier. So just a random mathematical equation. The point of an equation is that I can predict its value for any possible input. Okay, so that's what the equation does. Now, if it is put in recursion, if it's put in feedback loop, mathematically there is no shortcut to predict what happens after 1000 steps. Only thing I can do is I can actually run the model for 1000 steps, and then I will see what it does. If the model is fully deterministic, every time you run it for 1000 steps, it will do the same thing, but there is no prediction shortcut. You cannot quickly go there, so to speak. Okay, so that's quite important, and that's something that you will see with all complex systems. If you look at weather patterns, for example, what you get is that we can predict only very short time spans. Okay, which is typical here. So this unpredictability needs a bit more attention to understand exactly what it does. Okay, so typically we don't know whether these systems will grow or collapse, when they will, and how quickly they will grow or collapse. So with the World Wide Web, with the internet, there was evidently some people who thought this is great and it will grow out of proportion, but this could have not been proven earlier than the time when we saw it happen. And similarly, we have no clue about a potential collapse of such systems, right? So global trade supply chains, they kind of evade prediction. Nevertheless, they can become stable. And that's one of the reasons why it's worth studying this, because most of the things around us are complex systems. We actually have strict causality and predictability only in the laboratory, where we reduce variables, where we create very reliable reproduction of experiments. But other than that, in real life, in society, in biology, we have complex systems. So we cannot really predict them, but we can observe their properties. So you can see whether they're stable or not. Okay? And typically with the increase of growth factors, so I'll talk a bit more about this in the next lecture, but the growth factor is the key parameter, and typically the stability depends on the growth factor. So from a stable system, we can get into a chaotic system by increasing the growth factor. Now, in terms of the networks, it is crucial to understand that the size, the amount of elements in the network will change the property as well. So each element will remain the same, but if we have a huge amount of elements, typically the property of the network as a whole will change. Okay, and then there's a lot of theories and interesting things to consider here, but potentially one of the important concepts to introduce already is the concept of diffusion, which has to do with the ease of spreading data across the network, and we'll look at connectivity just now. So in classifying networks, we call for degree distribution, and we have a kind of a continuum from centralized networks to distributed networks. So with centralized, each node connects to the center, pretty much. With distributed, there is no center node, and there is dense connection between all the nodes among themselves. And we have a decentralized network, which typically involves clusters. Some nodes are more central than others. However, there is no absolute centrality, and there is no absolute distribution in the sense that many nodes will not have any connection to many other nodes in different areas. So let's look at these properties. I'm checking the time. I'm going to have to rush through this. So essentially, we have these three types. So centralized networks are ones we call scale-free or power law networks. Okay. So as you can imagine, most nodes will have only a few connections, and they will typically connect towards the center. And more central nodes will have increasing amount of connections. Yeah? Now, the interesting thing here is that we have a relationship between the degree of connectivity. So connectivity is the amount of connections, put simply, and the frequency of the occurrence of the node. Okay, so as the connectivity grows, okay, we actually get radically different properties. Okay, so for centralized networks, what you will have here, the connectivity degree is described with a number. So number of connections, essentially. Okay, so a quarter of the nodes, this is a kind of just a general picture here. A quarter will have a small connectivity degree, 2, a ninth, 3, and only a hundredth. So every hundredth node will have a degree of 10. So the larger the network, the higher the connectivity of the central node, as you might expect. Okay, so this is the kind of network that we're looking at, and one of the good examples here is the web. Okay, and here the search engines typically are the central nodes. However, you will find similar topologies or indeed properties in biology. Okay, fuel providing net molecules in metabolism of humans have similar properties. And the interesting thing here is that this network has a property which they called rich get richer, just to put it in simple terms, which is interesting because typically we would consider inequality in the society to be the responsibility of the few. However, in such networks, this always occurs. So the nodes with larger connectivity will increase their connectivity as the network develops. Nodes with lower connectivity will potentially reduce their connectivity as the network evolves. So you kind of get this separation as a property of a network rather than a responsibility of a node. Okay, so if we look at decentralized networks, so typically we get clustering, we get local hubs, and interesting things start happening here. Typically, if we look at society-related models, we get combining resources. We can have economy of scale because things are more efficient. We can have batch processing type behavior. And we have a term which is small world characteristic, which describes this. Essentially, it is a term that describes how we connect within the society, where we have a high clustering coefficient and very short average path lengths. Okay, so this is the idea that I can connect to any other person through very few handshakes, as they say, because even though people may be very distant in many ways, the connectivity of the network is such that the shortest path between two nodes is typically quite short. Okay, so here is a little statistic on this, and you can look up further ones. Now, distributed networks, okay, this is the type of network where we don't have any centralized control at all. We don't even get clustering. We kind of have equal node equality between the nodes. We have very high autonomy. The interesting properties of this type of networks is that they're very robust to failure. Okay, so there are no strategic, no critical nodes. So you cannot very easily attack or destroy this type of network because you actually have to deal with all the nodes. If you have a centralized network, it is sufficient to destroy the center and then the whole network fails. But if there is no center and you destroy one node or the other, the whole network doesn't even notice, so to speak. So it's much more robust. Okay, each node can be replaced or omitted. Certain tasks, batch processing type tasks, are more difficult to accomplish with this type of network. Typically, you would have slower diffusion. So as explained, that's the rate of information going through the network. You might have weak coordination, right? Because the diffusion is slow. Nevertheless, you will have a higher degree of adaptability. So these types of networks are probably the most dynamic in relation to the environment. Okay, and then finally, I'm out of time and we will talk about orbits in the next lecture. But in any case, it is interesting to observe that these networks, so basically just a computational scheme between a few nodes, will produce all these properties. And essentially, the evolution of a network like this is what we call an orbit. So it's a sequence of states that it goes through. I've talked about phase transition. So the point is that we can have chaotic phase, frozen phase. We will talk about these states in more detail. And indeed, the property of robustness, which is the property that network can sustain many perturbations, attacks, and so on and so forth. Okay, thank you for your attention, and I will see you shortly.